I have a problem. After dealing with rates over the last few weeks, I ended up going back and proving a number of facts about multiplication and comparing numbers that I'd been pretty certain were true, but hadn't actually proven before. In the process, I realized that I actually hadn't been thinking about comparing numbers as clearly as I'd thought I had, and there were some things about the process that I'd been assuming without having actually directly addressed them. These things felt important enough that I wanted to address them in full, rather than relegating them to the notes that I've been taking, keeping track of my progress. See, a few months ago, I woke up to realize that I'd forgotten all of mathematics, and could no longer understand equations, be they simple, quadratical, or anything else. Since then, I've been working to rebuild my knowledge of mathematics from scratch. To get myself on track, here's the definition that I'm using for comparing numbers. Given two numbers, a and b, I say that a is more than b if it's either the number after b or is after another number that's more than b, and that a is less than b if it's either the number before b or is before another number that's less than b. Numbers being before and after other numbers is something I can understand using the definition of numbers that I'm using. Every number has a number that comes after it, which is equal to that number plus 1, and every number except for 0 has a number before it, which is equal to that number minus 1. To start with, I want to prove these three statements about comparing numbers. They all seem like they should be obviously true, but that's only because I'm using numbers to model counting things. While at this point it's very unlikely, it still is technically possible that numbers being more or less doesn't necessarily correspond to them counting more or less things. I'll start with the first one, that given any two numbers, a and b, either a is more than b, a is less than b, or a is equal to b. To prove this, it should be enough to show three things. That a number a can't be more than itself, can't be less than itself, and that if a is more than b, it also can't be less than b. A isn't the number after a, or the number before a, from the definition of numbers. I know that the number before a is less than a, so as long as it can't also be more than a can't be more than itself. Similarly, since the number after a is more than a, as long as it can't also be less than a can't be less than itself. If I can prove that no number can be both more and less than another number, I've also proven that a number can't be more or less than itself. As for how to do that, I'll say that some number a is more than some other number b, and then see if it can also be less than b. Since it's more than b, I know it's either the number after b, or it's after another number that's more than b. In the former case, I know that it can't be the number before b, so the only way for it to also be less than b is for the number after it to be less than b. However, the number after it can't be the number before b either. So again, the only way for that number to be less than b is for a number after it to be less than b, and so on. Every number would have to be less than b for the number after b to be less than b. I think I know this can't be true, but things have gotten weird enough that I'm not quite sure. What if I tried doing this the other way around? If instead I say that a is less than b, and want to see if it can also be more than b, maybe I'll end up going the other direction. 0 doesn't have any other number less than it, so I know that it can't be more than any other number, which might make this easier to prove. Since a is less than b, it's either the number before b, or it comes before another number less than b. For it to also be more than b, it couldn't be the number after b, so the number before it would also have to be more than b. Sure enough, I can keep repeating this, and end up seeing that 0 would have to be more than b, which can't be true. So I can say that at least the number before b cannot be more than b. The other possibility is that a comes before another number less than b. What would have to be true for a to be more than b in that case? Well, since c is less than b, it's either the number before b or comes before another number less than b. And for c to be more than b, the number before c would have to be more than b. The number before c is a, though. I know a isn't b, but that a isn't more than b is the thing that I'm trying to prove. This approach clearly isn't working. What if I tried it in a different way? I can look at the number 0. 1 is after 0, so 1 is more than 0. 2 is after 1, which is more than 0, so 2 is more than 0. 3 is after 2, so 3 is more than 0, and so on, and I can say that every number is more than 0. 2 is after 1, so 2 is more than 1, and 3 is after 2, which is more than 1, so 3 is more than 1. 0 isn't after any other number, so it can't be after 1, or another number more than 1. So 0 isn't more than 1, but every other number is. How about 2? 3 is after 2, 4 is after 3, and so on. 0 isn't more than 2, so 1, which is after 0, can't be more than 2. Again, everything is more than 2, except for 0 and 1. I can use this process to find out exactly what numbers are more than any other number, but trying to do something similar for numbers less than other numbers is trickier. I don't have a number that doesn't come before any other number, so I can't anchor myself like I could with 0. In fact, now that I think about it, with the definition I've written, is it ever possible to show that a number isn't less than another number? The only way for a number not to be less than another number is for the number after it to not be less than another number. But there isn't any number that doesn't have a number after it. So there's nothing stopping it from being the case that every number is less than every other number after all. After all this time, I've come to the root of the problem. It wasn't just that I hadn't figured out the right technique or was messing up something with the proof, but in fact I've been working from a definition that meant the statement wasn't actually true. Way back when I was trying to define what it meant for a number to be more or less than another number, I picked this one because I thought it was the most clean looking, with two rules that perfectly mirror each other, and I thought that it was equivalent to the other possible definitions I'd come up with. But in fact, this definition doesn't work the way I need it to after all. Fortunately, based on what I've already proven, I think I can pretty easily fix my mistake. But it does come as a bit of a wake-up call. I can keep the rule for when a number is more than any other number, since 0 gives me a starting point, but for a number to be less than another number, I need to give myself a bit more. But where could my starting point be? I can't start with 0 again. Even if I say that, by definition, nothing is less than 0, that doesn't tell me anything about what numbers are less than 1, or 2, or anything else. I think I might need to change tactics entirely, and just say that less than means not more than or equal to. It feels like a bit of a cop-out, but any other approach that I could take would probably be at least as complex. As a bit of a compromise, how about this? I'll say that if I can prove the statement about numbers being less than other numbers that I was originally using for my definition by saying that less than means not more than or equal to, then I can use that for the definition. This way, I'll know that anything I used the old definition for will still work with the new definition. So I'll say that I have some number a and some other number b, and I want to show that a is not more than or equal to b, exactly when the number after A either is B or is another number that is not more than or equal to B. That's a bit cumbersome to say. I think I can break it down into smaller parts to make it easier to handle. I'm trying to show that either A is B, A is more than B, the number after A is B, or the number after A is not B and not more than B. If A is more than B, well, this is true, so I just need these other things to be false. I think I could reuse my earlier proof here, but just to be safe, I'm going to go over it again. A is more than B, so it's either the number after B, or after another number more than B. 0 isn't more than B, and by chaining together numbers after other numbers, I can say that any number up until the number after B isn't more than B. So A can't be B. A isn't the number before B, so the number after A can't be B, and the number after A comes after a number more than B, so is itself more than B. That's all good. Now on to the next step. If A is B, A can't be more than B, as I've already shown, and the number after A can't be B. The number after B is, by definition, more than B, so again, it's all good. If the number after A is B, again, A can't be B or more than B, and, well, the number after A is not B, so it's still good. And if the number after A is neither B nor more than B, well, I've already shown that none of the other things can be true. So the last thing I need to do is to show that it's never the case that none of these four things are true. If A isn't B, and isn't more than B, and the number after B is more than B, well, by definition, the number after A would have to be after B, or another number more than B, so this can't happen either. There was probably a neater way to do all of this, but I'm getting a bit paranoid about accidentally making my proofs too simple and running into problems like I'd been before. At some point, I should come up with a better way to write out proofs, maybe by labeling all the different rules and statements to keep track of which things I'm using to prove which other things. In any case, I've now proven that the statement I was originally using as a definition is true, if I use the new definition for a number being less than another number, so I can be confident using the new definition without having to discard any of my earlier work. Getting back to what I'd intended to only be the start of today, I've already proven that A can't be both more than B and equal to B, and now by definition it can't be less than B and also equal to or more than B, so that's the first one done. As for the next, if A is more than B, I know that it isn't equal to B, so the only way that it could be false is if B is also more than A. If A is the number after B, then I know that B has to be less than A, so it can't be more than A. And if it's after another number more than B, well, I can go some number of steps backwards from A until I reach the number after B. B isn't more than that number, so it can't be more than the number after it, and that applies all the way back up until I get to A again. Nice and simple. And as for the other one, this has been bothering me for a while now. I keep talking about, the first one, the next one, this other one. Especially now that I've gone through all this effort, I have a much better idea of how numbers have an order to them, from 0 to 1 to 2 and so on, and I should be able to use them as such. I'll keep first for meaning, well, the first thing in an ordered set of things, and I'll say that after the first comes the second, and then the third, and so on. This is much easier to keep track of. Anyway, getting back to, I guess, the third statement, if A is more than B, and B is more than C, well, I know that A can't be equal to C, I know C is less than B, and A is more than B, and C can't be both more than B and less than B. If A were less than C, then that would mean the number after A either is C or is another number less than C. The number after A is itself after a number more than B, so it has to also be more than B, and so can't be C. But that also applies to the number after that number, and the number after that number, and so on. I'd never get to C by going on past A. A, therefore, does have to be more than C after all, as expected. Today ended up being both more interesting and more tiring than expected. I'd thought that proving those three statements would just be a few minutes' work, but instead I realized that I'd been using a flawed definition for one of my foundational concepts. But then I did manage to patch the flaw in a way that didn't invalidate any of the work I'd done before. I'm glad it all worked out this time, but it's clear to me that at some point in the near future, I should spend some time coming up with a more standardized way to write out proofs, to hopefully catch situations like this more easily in the future.